So in the context of Martensite transformation, we have discussed about the shape deformation that is caused by this transformation, and we have seen that the deformation which brings about this change in the crystal structure or which is caused by this Martensite transformation is a combination of a dilatation which is perpendicular to the habit plane. So this is a uniaxial dilatation which is perpendicular to the habit plane, and then we also have a shear which is parallel to the habit plane. Okay, so the deformation that you have here, it's a combination of a shear parallel to the habit plane and a uniaxial dilatation which is perpendicular to the habit plane. Okay, and we have also seen that this deformation, this shear is an invariant plane strain which leaves the habit plane unchanged. Okay. On the other hand, we have seen that the deformation which actually transforms austenite to martensite is an invariant line strain. That is what the bend strain combined with a rigid body rotation would also give you. Okay. So the one which transforms austenite to martensite is actually an invariant line strain. So we have seen that there is this discrepancy, invariant line strain versus invariant plane strain, that we need to address. Okay. So this is one thing that we need to understand. We need to address the discrepancy here, that invariant plane strain is the one which is observed, but the one which actually transforms austenite to martensite is an invariant line strain. Okay. We have also discussed about the habit plane. Now there is something strange about the habit plane also, because it will come up with certain indices which look peculiar. For example, you can have a habit plane like 225 or 259, then 3, 10, 15. So these do not look like the familiar planes that we all know, we generally talk about, like 111 plane, 110 planes, and so on, right? The indices kind of look peculiar. In fact, these are irrational. These are approximated to integers, but actually these are irrational numbers. So this is another question that we have to ask and answer as to why the habit plane indices are like that, why they are irrational. Okay, so we have added one more question to our list, and today we are going to answer both of these, and as we do that, you will see how beautifully we can explain the mechanism of Martensite transformation. Okay. So we have seen that the bend strain combined with a rigid body rotation gives you an invariant line strain. So, this combination is an invariant line strain, and this correctly reproduces the orientation relationship. Okay. So, this generates the correct crystal structure for martensite. Okay. So, this we have seen before also, we have discussed it. So, we have seen that one of the lines here remains invariant as we combine the bend strain with a rigid body rotation. Okay. So, basically what we are saying here is that this is an ILS. I mean, this is leaving one line unrotated and undistorted. Okay. So, if I try and give you a little more clarity, we can look at this schematic as to what do I mean by saying that it leaves behind a line undistorted. So, we can look at that through this schematic here, where you see these two crystals, the parent and the product. Okay. Maybe I can color it differently. Okay, so here you can see that the strain which transforms austenite into martensite is an invariant line strain where one line at the interface remains unchanged. So, this is the line over here that you can see. This line remains undistorted. Okay. So, this is an ILS, this is an invariant line strain. But what actually is observed, as I said before, is an invariant plane strain. Okay. And that you can see from another schematic here. Here you can see that this plane remains invariant, a habit plane. Right. So, what is observed is an invariant plane strain, but what actually transforms the austenite to martensite is an invariant line strain. Okay. So, this is something that we need to address. So, this was addressed by a brilliant theory which was proposed back in 1950s. The theory is known as phenomenological theory of Martensite transformation or Sometimes it is also called as phenomenological theory of Martensite crystallography as well. So this was proposed in 1953 by Wexler, Lieberman, and Reed, and parallelly by Bowles and McKenzie. So apparently these two theories may look different, but they talk about the same thing. Okay. So therefore, this phenomenological theory of Martensite transformation is also sometimes referred to as WLR or BM theory. Both talk about the same thing, but maybe with a different approach to it. Okay. So this will actually address that discrepancy that we came up with. Okay, and now we can actually answer that as to why is that so, and how do you find it as an invariant plane strain when you actually observe martensite. So what we are saying is, if you have a austenite crystal like this, let's say, it transforms to martensite with a shape change. So we have seen that it is primarily a shear, right? Although a little bit of dilatation is there, a small amount of dilatation is also involved, but it is primarily shear. So the shape change would be something like this. So this is the correct or observed shape of martensite. Okay, but this is a wrong crystal structure, because in this case we have seen that this is an invariant plane strain, right? And an invariant plane strain cannot transform austenite into martensite with the correct crystal structure that martensite actually has. What we have seen is it is actually an invariant line strain which can transform austenite into martensite, right? But this is the wrong shape, because this does not generate the observed shape of martensite. This does not cause that change in the shape in this manner, right? This is the observed shape, but this shape is different from that, right? So although this is the right crystal structure, this is the correct crystal structure which will give you the correct orientation relationships also, but the shape is wrong. Okay. So how do we correct it? Because ultimately this has to turn into this, right? Because that is what is actually observed. So this is an invariant line strain and this is an invariant plane strain. Now let's say if you have two invariant plane strain, the intersection of two invariant plane is an invariant line. Okay, something like this. If you look at this diagram now, let's say this is one invariant plane and there is another one over here. So the intersection of two invariant planes is an invariant line, right? In other words, an invariant line strain can be factorized into two invariant plane strain. Okay. So therefore, if I add one more shear here, then this becomes an invariant line strain. So these two shear that we have now, this was the first one. We can call that as P1, which has transformed this shape. And then, since it's an invariant plane strain, but we need to actually have an invariant line strain for the austenite to transform to Martensite, we can add another invariant plane strain, which is again a shear that would give rise to an invariant line strain, which is also same as this, right? A combination of bend strain and a rigid body rotation had also given us the same thing, an invariant line strain. Okay. But we still have a problem here, because although we have obtained the right crystal structure, this shape is not the right one, not the observed one, right? So we need to correct this shape to the one which is actually observed, right? So this shape has to change without changing the crystal structure, because we have already obtained the right crystal structure now when we have come to an invariant line strain, right? So how do I do that? How do I change the shape without changing the crystal structure? So what kind of deformation can give you a change only in shape without changing the crystal structure? Have we discussed something like that before? Do you remember this slide? What I said about slip, I think it is probably written there on the right hand side top corner. If you see, slip causes deformation, a macroscopic shape change that you actually see when you deform a metal, but it does not cause any change in the crystal structure, right? So slip is a process which can change the shape but does not change the crystal structure, does not change the crystal lattice, right? So it's a lattice invariant deformation in that sense. Okay. Now, sleep is one form of one of the most dominant forms of plastic deformation in metals, but there is one more form, there is one more mode through which metals can deform, and that is twinning. So this is again the same thing, it will change the macroscopic shape, but it does not change the crystal structure. So this is also a lattice invariant deformation. Slip we have already seen before, so let me talk a little bit about twinning also. So if this is a crystal, and if we apply a shear, then it can also deform in this manner rather than slipping, where you could see that it has deformed across these two planes shown by those two dotted lines. Okay, these two planes were like this. And now if you look across them, you would see that the crystal has deformed when this shear is applied. Okay, so you can see a macroscopic shape change here also. But this is not a slip. If you look at across this plane, you would see there is a change in the orientation in one manner, and then across another plane there is a change in the orientation, but it is exactly in opposite manner. You would also find that if you look across this plane, which is known as the twin plane, this region will be the exact mirror image of the parent crystal above it. Similarly, if you look across this plane, this region will be a mirror image of the crystal which is here below it. Okay, so this acts like a mirror plane, and this region is the twin. The shaded area that you see here, that's the twin, and these are two twin planes. It is something like this, where these are the crystal planes where the atoms are arranged in a particular pattern. So this is the parent matrix, and this is the twin plane over here, and another here. And in between you have the twin, right? So you can see that the orientation of the crystal across this twin plane has changed, and in the twin region the orientation is a mirror image of the parent lattice. Okay, and you can see that the twin is bound by two twin boundaries. So when you observe a twin under a microscope, it will always appear as a pair of lines. So let's say these are the grains, and if you find a twin in the microstructure, this will appear as lines or a band like this. So these are basically those two twin boundaries. And inside these two boundaries you have the twin. And we will see the relevance of this in the context of Martensite transformation. That is why I just wanted to show this. Okay. Now let me quickly come to this as to how you can correct this shape to the right shape. Okay. So if we can have a lattice invariant shear such as slip or twinning being applied here, then this will cancel the shape change due to the second shear, and the correct observed shape would be obtained, because a slip or twinning will only change the shape without changing the crystal structure, right? And now you can also answer the question as to why the habit plane has those peculiar kind of indices. So the crystal has to go through a lattice invariant shear to get the correct shape. And this lattice invariant shear is either through slip or twinning, as we discussed. If you look at this diagram, for example, this one, here the lattice invariant deformation has taken place by slip. So you can see those small slip steps such as here and here for the shape to recover to the observed macroscopic shape. And this one here, twinning has taken place for the shape recovery. So you can see this twin here, for example, through which the shape has recovered to the observed macroscopic shape of Martensite. So a consequence of this is that the habit plane indices are not rational, because the amount of lattice invariant shear which is needed to recover the macroscopic shape is in itself not rational. Okay. Moreover, as you can see from these diagrams, the habit plane, which is here, and here, is corrected for the distortion by the lattice invariant shear, but it is a plane of zero distortion only on a macroscopic scale. Okay, and therefore the indices could be irrational numbers. Okay, you can see the same thing from the following schematic as well. So if it is a twinned crystal, if it is a twinned martensite, so you can see that it has gone through that lattice invariant shear through twinning, and it has obtained that correct macroscopic shape. So here these facets, this one or this one, may be rational, but the average plane, which is this one, is not rational. So the overall plane after the lattice invariant deformation is not rational. Similarly, if you have a slipped martensite, you can see those slip steps, and the average plane that comes out from here after the adjustments through slip to get into the right macroscopic shape is again irrational, right? Okay, so this theory thus also explains as to why the habit plane has those kind of peculiar indices such as 3, 10, 15 and so on. So in summary, basically what we have in this Martensite transformation in terms of the mechanism is an invariant plane strain P1, which is combined with another invariant plane strain P2, both of which are shear, which generate the right crystal structure. But the shape is wrong. And when this is combined with a lattice invariant shear like slip or twin, the shape is corrected to what is actually being observed. And we have a martensite crystal with the right structure and the correct shape. Okay.